Welcome back to Stats Online. Today's topic is hypotheses testing of a single mean value. Today we're just introducing the concepts. And toward doing that, I have a couple of examples. The first one says Toyota claims that on average, their Prius gets a combined 50 miles per gallon. All right, that's city and highway driving. Well, you could imagine a consumer interest group, right, wanting to test this claim. All right, they want to do a hypothesis test of this claim. To do so, they sample a fleet of vehicles. All right, and hopefully that fleet of vehicles would represent the population of interest, and they would drive these vehicles under different conditions, different geographical areas, different weather patterns, and come up with a sample mean. Okay, and this average, this sample average, would then be compared to the manufacturer's claim average of 50. All right, and either we find evidence of support of that claim or evidence against, and we'll talk about what to do or the kind of the decision space with these examples. Another one, the Starbucks desires to keep their caffeine content to an average of 330 milligrams for a grande brewed coffee. All right, so that's their medium cup of coffee. And so, of course, the caffeine content to a cup of coffee is variable. It varies on how much the different beans, but also how long the beans are roasted, the machine that's used in producing the coffee. And all of these things have a little bit of variability built in. And so it's kind of a quality control. Again, you could imagine Starbucks or someone who's contracted from Starbucks sampling cups of coffee in different environments, different locations, different stores, different beans to make sure that their average is within their desired average. Okay, and if it's not, right, if they reject the underlying hypothesis, then maybe they want to recalibrate machines or choose different inputs into production. Okay. All right. So basically, there are two elements of hypothesis testing that are important here in terms of framing the problem. And the first is the null hypothesis. Okay. The null hypothesis is a statement about the true value of the population parameter. All right. It's a numeric value. It's that 50 miles per gallon in the Toyota example. It's that 330 milligrams in the caffeine example. So we need a number, okay? And we have some notation here that I guess is slightly new. The H sub 0 or H naught indicates the null hypothesis. And mu, of course, is that population mean, all right, without the subscript, equals, and then this is the placeholder for the number, right? So this mu sub 0 or mu sub naught, this is the placeholder that we need a numeric value at. All right, so if we're using that Toyota example, mu would equal 50. This could be a formulation for the null. That's kind of the benefit of the doubt of Toyota in this case would go into the null hypothesis. Now, one important element here is that equal to, right? Some version of equal to has to be part of the null hypothesis. This is kind of the equivalent sign here for our example, but we could also have these weak inequalities of greater than or equal to or less than or equal to. So those are the three possibilities that exhaust the symbols or the signs that go into the null hypothesis. Okay, and the way to think about the null is really kind of the status quo or the benefit of the doubt in terms of these manufacturers' claims. The alternative hypothesis, parameter values if the null is not true. So it has to encompass everything that is outside of what's captured in the null. So here our example for the null hypothesis that the population mean is 50. We would have to have a case in the alternative that the population is not equal to 50. It could be less than or greater than, and not equal to would capture that. Now, the trick is, or the thing to keep in mind that and this is something that many students get confused with, is that the alternative hypothesis is actually what you're testing. It's actually your research question, okay? And so the alternative hypothesis is really, something different from the status quo, something different from the benefit of the doubt, and so it's really kind of the research question at hand. So the notation for the Toyota example would be mu not equal to 50, and there we'd have a null of mu equals 50, an alternative where mu does not equal 50, and that captures, of course, all possibilities. And we could also have greater than and less than, greater than the symbol that would be attached to a null of less than or equal to, and less than for an alternative would correspond to a null of greater than or equal to. All right. The point is, with the null and the alternative combined, all options have to be exhausted. So we'll complete a couple or two examples. Starbucks does not want to brew coffee with too much or too little caffeine. So you can imagine a following null and alternative hypothesis. The null is kind of the status quo, the benefit of the doubt, that the average caffeine content in a cup of grande coffee is 330 milligrams. The alternative is that something different. The alternative is that it's something different. Notice the sub A for my alternative hypothesis. This is what you call a two-tailed test, right? This would be a test if Starbucks is interested if it's something different from 330. They don't care necessarily if it's dramatically above or below. They just care if it's different, right? So they're not just interested if consumers are getting too much caffeine, or too little caffeine. Both would be considered problematic, and so they're interested in both directions. A two-tailed test. And so, again, the alternative is the research hypothesis, right? We're seeing if it's something different from the claim. Now, if mu is not equal to 330, then we need to adjust the brew. That part is kind of the subjective nature of this, right? Of course, Starbucks could use objective statistics to figure out whether they think there's a problem, but then what to do after that is subjective. Toyota claims an average of 50 miles per gallon. Let's say we want to test whether their cars actually get less than 50 miles per gallon. You could consider if their cars are actually more fuel efficient than it's marketed as or advertised, that's probably not a problem. But if consumers are actually getting duped and on average these cars are getting less than 50 miles per gallon, that's probably a problem. And so what we're really interested in, our research hypothesis, is the average less than 50. And so that's what we're going to frame the alternative with, right? You'll notice that the alternative is mu less than 50 miles per gallon. And the null, okay, is greater than or equal to. We're allowing it to be equal to their manufacturer claim, or anything above it is also fine for this directional hypothesis. And this is called a one-tail test, because we're only really interested in one tail of the distribution. In this case, areas less than or to the left of the stated 50 miles per gallon. All right, again, the alternative is the research hypothesis. If mu is lower than 50, right, if we find evidence in favor of that alternative, or if we reject the null, then Toyota may need to revise its claim. Now, with hypothesis testing, the conclusion space is pretty simple. In fact, there are two possible conclusions. You can either reject the null hypothesis or fail to reject the null hypothesis. All right? So if I reject the null hypothesis, that means I'm finding evidence in favor of my alternative. So rejecting means in favor of the alternative. And failing to reject the null means finding evidence in favor of the null. All right, so that jargon can be a little bit confusing, but again, there are only two possible conclusions you can make, and so that simplifies your life in some degree. Now, the two decisions are always stated in terms of the null, right? Rejecting the null, you conclude that HO is wrong, your data support the alternative, okay? Or if you fail to reject, you cannot conclude HO is wrong. But we never use the word accept. We don't say we accept or we prove. We're, again, going to be taking a single sample and making a decision from that sample. But we recognize that there's sampling error, right? We've only drawn a subset from a population. And so we're not proving anything. We're finding evidence in support or against. Now, if there are two types of decisions you can make, it follows that there are going to be two types of errors. All right, there are two ways that your decision can be wrong. Well, that's the case ex ante. Now, ex post, there's only one way. You're either correct or you're wrong, and you're either wrong in one dimension. But before you conclude your hypothesis test, before you draw your data, before anything, you know that there are two potential errors. Type 1 error is when you reject the null hypothesis and it was actually true. All right, you found evidence against it, but the hypothesis, the null value is actually true. And this kind of error is the type 1, and I remember this as RR, or RA, and the RR stands for rejecting when it was right. Okay? The type 2 error, the second type, is when you fail to reject a null that you should have. Okay? You failed to reject a null when it was false. So I remember this as FF or FA, and failed to reject when false. So we can put these relationships of the two decisions to the truth in a quadrant. All right. In the first column, we have our decision space, reject or fail to reject, and this is of course in reference to the null. And then the null hypothesis is the state of the world that you don't know you're in or not, is either true or false, right? And if you reject a null hypothesis that's actually true, you've made that first type of error, where rejecting something that's right, type 1. If you fail to reject it when it's true, then you made that correct decision, right? We don't accept it, we fail to reject it. You've also made a correct decision when you reject something that's false, right? It's not true, you rejected it, you did the right thing. The type 2 error is when you fail to reject a null hypothesis when it's actually false. You should have rejected it. All right, so that's basically where we'll be in one of these quadrants. This example, which I'm calling a non-stats example, simply because there's no numeric value that we're testing, is about O.J. Simpson. This is about O.J. Simpson's first highly publicized crime. He eventually wasn't convicted of this crime, but allegedly he had killed his ex-wife and her husband or boyfriend at the time. And long story short, O.J. Simpson got off and was not found guilty. All right. However, there's been a long-standing suspicion that potentially he got off or got away with murder. Contributing to that was the book that he published years later called If I Did It, where he outlined how he did it. Anyway, let's consider the case that the null hypothesis is that O.J. is not guilty, the benefit of the doubt, and the alternative hypothesis that O.J. is guilty, okay, that he did do it. And if we consider what happened, right, he was found not guilty. Okay, he was found not guilty. Below here on the slide, if O.J. did do it, if he did actually do the double homicide, then what kind of error did the judge or the jury, more precisely, make? And the answer to this question is C, a type 2 error. And the reason is that the null hypothesis, if O.J. did do it, is that the null is false, right? The null says he's guilty, but he's actually not guilty. I mean, the null says that he's not guilty, but he actually is guilty. And so therefore, the null hypothesis is false, but the jury fails to reject it. And so that would be a type 2 error that the jury made in this case.